Here's your video for understanding exponential models. We want to know that exponential models do repeated multiplication. This connects to something that we know already about exponents, that it's a way to show repeated multiplication. Like if you take the number 2 and multiply by 2 over and over, we can use an exponent to represent a repeated multiplication. 2 times 2 times 2 times 2 times 2, we see it there 5 times. We can write that as 2 to the 5th power. We can also evaluate that exponent. 2 to the 5th power equals 32, which we can see from the repeated multiplication. 2 times 2 is 4, 4 times another 2 is 8, 8 times 2 is 16, 16 times 2 equals 32. But when we're working with models, we're trying to show some kind of change that's happening. So what sort of change are we talking about when we say a 2 is repeated over and over and over? Think about starting with a number like 10. If we start with 10 and multiply by 2 over and over a total of 5 times, what does multiplying by 2 do to a number? It doubles the number. So a 2 over and over and over is showing that we're doubling what we started with over and over, a total of 5 times. Now there isn't a way to use an exponent to put this entire multiplication together, because exponents are only when we have the same number multiplied over and over, and that number is called the base. But what we can do is write 10 times 2 to the 5th power. The repeated 2's become the exponential expression 2 to the 5th power, and we started with 10, and we still see that we're starting with 10. And the meaning of all those times 2's is doubling. So we have 10 times 2 to make 20, doubled again to make 40, again to make 80, doubled again to make 160, and then doubled one last time to make 320. Now we know that 2 to the 5th power is 32, and 10 times 32 equals 320. As we deal more with exponential models, we will be looking for some starting amount, and then what kind of repeated change do we see that we want to accomplish with a repeated multiplication. If it's doubling, then we want to repeatedly times 2. This would be what you could call exponential growth, a repeated multiplication to change your starting number to some final result. Now, repeated multiplication won't always give you exponential growth. Think about multiplying 0.5 or 1/2 over and over and over. Written this way, we could write it with an exponential expression. We've got 0.5 to the 5th power. But now think about what sort of a change do we make when we multiply a number by 0.5. Think about starting with 160,000. What's the result of multiplying 160,000 by 0.5 to the 5th power? Well, we want to know about the repeated multiplication. And multiplying by 0.5 is a way to cut something in half. So we've cut it in half 5 times. The first time from 160,000 down to 80,000, and then down to 40,000, and then 20,000, and then 10,000, and the last, multiply by 0.5, cuts us in half from 10,000 down to 5,000. So we use these exponential expressions and exponential models to talk about some kind of repeated change that happens through multiplication, which could mean doubling, or it could mean cutting in half, multiply by 0.5 or 1/2 over and over. But we also use percents a lot when it comes to multiplying by numbers to create some sort of change, either a percent increase or a decrease. So let's talk a little bit more about these percent changes. When you're working with percents, you can figure that you start every situation at 100%, refers to the whole number, one whole, and when we multiply by percents to calculate a percent change, we change that percent into a decimal. So we would be multiplying by one whole, 1.00. I just kept the 2 zeros so it looks a lot like 100%, just with the decimal point moved over 2 places to the left. And that happens because percent means out of 100. So 100% is like a fraction 100 over 100, which is one whole. It's important for us to realize that we start each situation at 100% because that helps us understand how to work with percent changes, like a percent decrease of 30%. This could apply to a store that's having a 30% off sale, or your paycheck where 30% comes off to go toward taxes. But when you start at 100%, a 30% decrease brings you down to 70%. So a 30% decrease is exactly the same as saying 70% of the number you started with. And you can calculate that by multiplying your number by 0.7. If we're dealing with a situation that has a percent increase, like a 20% increase, if you start at 100%, then a 20% increase gets you to 120%. We're just adding the 20% to 100%. In the case of the decrease, we were subtracting 100 minus 30 to get the 70%. We still want to look at the decimal numbers, so 120% would be 1.2. If we wanted to calculate a 20% increase, we could multiply by 1.2, because a 20% increase is 20% above 100, up to 120. So we had just looked at when it might be useful to repeatedly multiply by 2 for doubling, or repeatedly multiply by 0.5 to cut in half. But working with percents, we can see all sorts of other numbers that we might want to use in a multiplication. And a repeated multiplication, if, for example, we wanted to talk about something that increased by 20% each year, or each month, or just a repeated increase. Or we would use 0.7 to multiply by a number to do a 30% decrease. Because remember, 30% decrease when you start at 100% leaves you at 70%. And if a quantity decreased by 30% repeatedly, like the value of your new car decreases by 30% each year, then we could repeatedly multiply by 0.7. Each time we multiply by 0.7, that's a 30% decrease. So repeated multiplication of 0.7 will do a repeated 30% decrease. So 100%, or 1 whole, is where we start off. Any number, there's my variable, this time it's a happy face, any number times 1, of course, equals that same number. But when we multiply a number by a number less than 1, like 0.7, which we know connects to a decrease from 100%, we're going to get a result that is a 30% decrease, or 70% of what we started with. And that same number multiplied by 1.2 is going to give it a 20% increase. Percents are one of the most common ways to talk about multiplicative change, a change that we see when we can multiply by some number. We should know now that if you were to multiply by 1.2, as a percent, that's 120%, so you're talking about a 20% increase. Or if we see multiplying by 0.7, we know that that's a 30% decrease. 0.7 is 70%, but as you always start at 100%, you can get to 70 with a 30% decrease. And we can certainly work with all sorts of other numbers with percent increases and decreases. For example, we could do a 5.9% decrease. Starting at 100%, subtracting 5.9% equals 94.1%. And then as a decimal, we would use 0.941. And we could multiply a number by 0.941 to decrease it by 5.9%. And even if we have a very, very small decrease, like 0.9%, take the same approach. 100% minus 0.9% leaves us with 99.1%. So we would use the decimal 0.991. And multiplying by 0.991 accomplishes a 0.9% decrease. To increase a number by 3.8%, we know starting at 100%, this time we are adding for the increase. And 3.8 plus 100% equals 103.8%. There's our increase from 100% by 3.8 up to 103.8. And write that number as a decimal, and multiplying any number by 1.038 will increase it by 3.8%. Let's say, for example, that you're investing $500 and that it increases by 1.29% each year. First, we need to take this percent and see that we have an increase. So from 100%, a 1.29% increase equals 101.29%. And as a decimal, because we're about to use it in multiplication, 1.0129. So to calculate the amount of this investment, starting with $500, to increase it by 1.29%, we can multiply by 1.0129. This gives us the amount in the account after 1 year, increasing by 1.29% just once. It gives us $506.45. If we want to know the value of this investment after a second year, that means starting with $500, we've multiplied by 1.0129 twice, for the first year and then again for the second year. This equals about $512.98. So an exponential model would be a way for us to show how we could calculate the value of this investment without specifically talking about a number of years. We know that we would start with the $500 investment, that each time we want to increase by 1.29%, we would multiply by 1.0129, and the way that we would show a repeated multiplication would be with an exponent. Now in this scenario, we're doing this multiplication, this percent increase, once per year. So our exponent should be how many years, because the exponent is how many times should we do this multiplication, do the percent increase. We want to do it for each year, so we'll use the exponent t for time and say that t equals the years. Here's another example. A $23,000 car depreciates by 11.3% each year. Depreciating means that it decreases in value. So when we look at our percent change, we're looking at a decrease. From 100%, we're decreasing by 11.3%. That leaves us with 88.7%. So we're multiplying by 0.887 to do the 11.3% decrease. The value of this car after just 1 year would mean, starting at $23,000, we're going to multiply by 0.887 just once. It equals $20,401. To find the value of the car in the second year, we could take the $20,401 and multiply by another 0.887, and we should also know that starting with the $23,000, it means we're multiplying by 0.887 twice. Each time, we're calculating an 11.3% decrease, and it equals about $18,096. So our exponential model for the amount of the value of this car, starting with $23,000, we would multiply by 0.887 for each year. So we could use the exponent to represent years, so that each year represents multiplying by another 0.887, which is an 11.3% decrease. Here are two situations for you to try, so you can pause the video and try these two. And we want to come up with the actual exponential models, so not a calculation of a value for a specific number of years, but a formula or an equation where we say what is the amount, and we use the variable t to represent time. And I think we see growth per year, so we're going to be using t equals how many years. So pause the video and try these two, and then restart, and we'll go through the answers. In the first example, we're starting with $1,200, and we have a very small 0.79% increase. Well, starting at 100% and adding 0.79%, it takes us to 100.79%. So as a decimal, that is 1.0079. And the exponent, how many times should we do this percent increase? We want to do it for each year. In this situation, it was a percent decrease of 8.5%. So our amount would again start at $1,200, but an 8.5% decrease from 100%, taking away 8.5%, leaves us with 91.5%. So as a decimal, we're using 0.915. But still, the exponent tells us how many times to do that multiplication, which does the 8.5% decrease.